Welcome everyone to the second session of the first day, and we are very happy to have Sergei Gukov from Caltech and Paolo Bedake from the University of Maryland. So we'll have a 40-minute talk followed by a 15-minute discussion, and we'll start with Sergei. So all yours.
Oh, thank you very much for the invitation, and thank you to all of the organizers for this nice reunion. It's definitely nice to be back, even virtually. So I'll try to share my screen. I hope it works. Let's go to full screen mode. So the subject of my talk will be resurgence in Chern-Simons theory, and it will share the full features of interacting quantum field theory. Namely, we'll start with the perturbative series, which will be computed using Feynman diagrams and the usual technology of quantum field theory that we learn in textbooks. And it has its other foot firmly rooted in topology, which will provide some techniques that will aid QFT computations, in fact, and also QFT will feed in to provide some intuition for topology. So this interaction between mathematics and quantum field theory will be very fruitful in my talk, going both ways. So we'll start with the perturbative series, which is a formal series and a coupling constant, and because its coefficients are growing very fast, it's divergent. So resurgence is this magic tool which allows us to not only make sense of this series, but it also tells us that the divergence of the perturbative series is not just meaningless divergence, it actually has wealth of information encoded in it. It has a non-perturbative effect, and if done properly with perhaps additional information, can be resummed into exact answers. So that's going to be the goal of our discussion today. This magical tool comes with lots of interesting, fun facts and problems. So this is an example of such problem, which I learned from David's 2014 lectures, or Introduction to Resurgence. According to Poincaré, if you show these two versions of series to physicists and mathematicians of his time, Poincaré says that they would have completely different conclusion regarding the convergence properties of these two series. Mathematicians would conclude that the first series is convergent, whereas physicists, or Poincaré says astronomers, would actually conclude that the second one is convergent because the first few terms of the second series decrease very rapidly. So this is a kind of fun fact, and one of the first few things that you learn in the beginning or along with resurgence. And there are many great resources and many such stories and examples that you can find in the literature. So when I was working with Marcos Marinia and Pavel Butrov, I learned a lot from Marcos's lectures on non-perturbative effects. Then Maxime gave many lectures over the years, and I was lucky to witness or be present in some of them in person. I think many of them are recorded, which makes them a great resource, especially now when everything is online. And then there are many other resources and lecture notes, which I listed here, various aspects of which will be related to what I'll talk about. Resurgence in Chern-Simons theory specifically also has a fairly long history. It goes back to some of the pioneering works of Lorenz, Zagier, Hikami, and others, where various calculations were done without even using the word resurgence, but they're very similar in spirit and in fact very influential for what happened next. This is roughly a summary of some of the most prominent works that influenced discussions at our 2017 KITP program. And part of it was a series of papers by Edward Witten, which were very influential and stimulated many results in our program. Then you also see names of Marcos Marinho, Stavros Garofalidis, and many other people you know featuring prominently. So these were some of the foundational works that already applied resurgence in the context of Chern-Simons theory, and Here I want to be maximally inclusive, so if you see any important development that I missed, please send me email later after the talk. One of the main outcomes of these developments, which we did discuss a few years ago, was how to start with perturbative series in coupling constant. I'll call the coupling constant H bar in Chern-Simons theory, and using Borel summation and resurgence, produce a non-perturbative answer, which is a function of variable q written as exponential of H bar. So this interplay between perturbative, non-perturbative, or formal power series expansion and an exact function will be the main feature of our discussion today. But unlike reviewing some of these developments leading into the program, I'll try to look back and summarize various aspects of what happened after the program, since the KITP program a few years ago. So again, these are some of the papers that studied resurgence in the context of Chern-Simons theory. And one of these papers, for example, was already mentioned in Daniela's talk earlier this morning. It actually was done, initiated, and partly done at KITP. But to disappointment of the authors, I won't really be talking about this paper. In fact, I'll try to touch upon various aspects of many of these papers and kind of summarize what we learned and what are the future directions. In particular, I'll try to present 5 prospects that came out of this research, and I'll try to present 5 open questions. There'll be questions that, in my opinion, are interesting for further study. As you can see, this is a fairly young subject that involves lots of young people, and even young Anders, and everybody who knows him knows that he's very young at heart. So it will be a pleasure to summarize work of many young people here. So, as I mentioned before, Chern-Simons theory is, first of all, a quantum field theory. So therefore, if you want to compute perturbative series in coupling constant H bar, we can use Feynman diagrams and standard techniques from textbooks, the way Mr. Feynman taught us. So this is one of the papers on perturbative Chern-Simons theory, which is more than 30 years old. It shows here completely standard Feynman diagrams. This is figure 3 from the paper. And using this sort of techniques, we can actually go ahead and compute loop amplitudes in Chern-Simons theory on any 3 manifold. So this is completely doable and a normal problem from the QFT point of view. However, those of us who teach to QFT or study quantum field theory know that going beyond 2-loop, 3-loop approximation is usually pretty hard. So you're often lucky if you can get a 4-loop or 5-loop answer. So this is a typical slide that you may see from lectures of either S.V. Byrne or Lance Dixon, where they try to illustrate that Feynman diagrams are really hard. So to get a simple answer, such as the one written on top of the page, you need to list many different Feynman diagrams and calculate their answers, which takes, in this case, 24 pages and small font like this. So the problem quickly becomes intractable and fairly complicated. So even if we want to apply resurgence to perturbative expansion in general quantum field theory, we usually are limited by computational power of producing perturbative series. This is actually where interaction with topology comes to the rescue. According to the theorem, any 3 manifold can be obtained by performing a surgery on a knot or a link. So as a result, the study of 3 manifolds, and in particular Chern-Simons theory on 3 manifolds, can be reduced to a 2-step process. You first study what happens for knots, and then you ask what happens under surgery operations, namely cutting and gluing. So here is an example of a surgery on figure 8 knot. It's a particular manifold. So according to this theorem, all manifolds will be labeled by basically knots with integer or fractional labels. So these are surgery coefficients. And the theorem says that even fractional coefficients like this, say for 17th, can be represented by a different link, maybe with more components, such that all of its components are labeled by integers. So this integers encode how we do surgery, or in different words, cutting and gluing. So why is it useful? First of all, any three-manifold can be constructed in this way. So therefore, we can reduce the problem to knots. And if you know the surgery machinery, surgery formulae, then we're basically done. We can compute the answer for any three-manifold. And this will apply in my talk to both perturbative series, which is series in H bar, and then we'll talk about analogous formulae, surgery formulae, in terms of Q series. That's going to be non-perturbative answer. For the perturbative series, this is basically one-line formula. It may look somewhat involved, but its structure is actually very simple. And if you ask me later after the talk, I'll show you Mathematica code which implements it. It's, again, one line of code. It's extremely straightforward. And what it takes as an input is the data of the knot. So these coefficients, labeled by integer m, are somewhat simple. So here they're shown for various knots: trefoil, left, right-handed, figure 8 knot, and so on. There are such coefficients that are known for any knot. And if you want to perform a surgery, you can produce your perturbative series in H bar simply by feeding the right knot and picking the right surgery coefficient. And the formula spits out an answer, which is power series in H bar. As you can see, the coefficients are growing pretty fast. They are not integers. They're actually not that exciting at all. But the point here is that this perturbative series in coupling constant H bar is extremely computable. So this is what makes Chern-Simons theory special, that you can compute way beyond 4 or 5 loop answer that we usually have in the garden variety gauge theory. We can go up to 100 loop order in a split of a second. So that's very straightforward. So therefore, there is a lot of data, and it may be tempting already at this stage to expand this to H bar to 100 or several hundred order in perturbative expansion, and ask what will happen to the Borel resummation, resurgent analysis in this context, and so on. I have to point out that this formula is also quite nice. It has meaning in topology. I learned it mostly from our work with Marcos and Pavel, but it also appeared in closely related context and topology in works of Belikova, Tangle, and other people. Before I apply this resurgence technology to perturbative expansion like this, it's important to point out several other aspects which will be good to know in terms of what to expect. Namely, there are many problems, such as trigonometric integrable systems, gauge theories in dimension 3 or higher, open topological strings, or any problem, in fact, that involves a spectral curve in C star cross C star. They all share one curious feature. Namely, their classical phase space or configuration space is not simply connected. So this fact that in all of these problems, configuration space is not simply connected has profound effects on the exact WKB approximation as well as resurgence. Each saddle point comes in an infinite set of towers of saddle points replicated infinitely many times. Here, when I talk about Chern-Simons theory or gauge theory in 3 dimensions, I actually mean both Chern-Simons theory as well as some physical theories such as supersymmetric 3D n equals 2 theory, which can be related to it by 3D correspondence. In the later context, the configuration space or field space is also not simply connected, and manifestation of this is that we usually write saddle point equations in terms of exponentiated derivative of the twisted superpotential. So the twisted superpotential has to be exponentiated to find the saddle points, and these equations are sometimes known as beta equations in this context. In all of these cases, because the configuration space or field space is not simply connected, the corresponding action functional or Morse function, if you think about it that way, is actually circle valued. or if you work on a covering space, is multi-valued. And the story of Picard-Lefschetz theory or Morse theory with multi-valued or circle-valued Morse functions has a very long history. So here is one of the famous papers in the subject. It's written by Sergei, but the date of this work is 1981, so definitely this is not me, that's another Sergei. This word here on top is mathematics, and this is the paper by Sergei Novikov, who was studying Picard-Lefschetz theory and Morse theory with circle-valued Morse functions. Namely, his goal was to understand how to recover cohomology of the space, and this is very important for understanding gradient flows and Lefschetz symbols in the context of a periodic Morse function. So if you know, if you heard about Novikov rings, this is part of the same subject. It's very rich and very interesting, and is quite a bit more delicate than usual Picard-Lefschetz theory or Morse theory with single-valued Morse functions. As I mentioned, it has several interesting features. First of all, each saddle point is replicated infinitely many times. So that leads to periodicity on a Borel plane, which we already saw earlier today in Maxim's talk. And as I'll try to explain in the context of Chern-Simons theory, this actually leads to new Q-series invariants of knots and free manifolds that invariance limits can recover familiar invariants such as Witten-Reshetikhin-Turaev invariants, logarithmic knot invariants, or other ones. It involves other features such as distinction between Gaussian and non-Gaussian saddles. In Chern-Simons theory, a trivial flat connection is always a solution to equations of motion, and because it's fixed by the entire gauge group, it's actually non-Gaussian saddle points. So non-Gaussian saddles or abelian flat connections are unavoidable in the story and play an important role. Another feature that I want to point out here is that this infinite sequence of saddles, this towers, sometimes leads you to problems where you need to resum or take a sum of infinitely many copies of the Stokes coefficients or trans-series coefficients. Each Stokes or trans-series coefficient usually is integer. It can be understood as intersection of Lefschetz symbols. But when you take a sum of infinitely many of them, what happens is the answer is non-integer. So as is well known, if you take a sum of finitely many integers, you get an integer. If you take a sum of infinitely many integers, you get a non-integer answer. And this is actually quite interesting and important for integrality of the Q-series. So ironically, this non-integer fact here has to do with integrality of the Q-series itself in a very peculiar and tricky way. I leave it to you as an exercise to figure out the right-hand side of both of these integer and non-integer calculations here. So this leads us to our first lesson. I promised you 5 prospects and 5 questions in Resurgence applied to Chern-Simons theory. So the first prospect and lesson is that abelian flat connections, or more precisely spin C structures, play a very important role. And after Borel resummation, what you find is new Q-series invariants of 3 manifolds. So you get exact answer, which is a power series in Q, which are labeled by abelian flat connections or spin C structures. Abelian flat connections and spin C structures are close cousins of each other. The distinction is not large, and if you don't know much about spin C structures, you can think of both of them as just being elements of H1, the first homology of the 3 manifold. So this Q-series invariants labeled by spin C structures or abelian flat connections serve as atoms for building more interesting invariants. For example, if you sum over these labels with suitable coefficients and take the limit where Q goes to root of unity, you can actually recover familiar Witten-Reshetikhin-Turaev invariants at level K if you consider Kth root of unity. On the other hand, if you take a limit Q goes to 1 and bone sum over this additional labels, these spin C structures, you actually recover Turaev torsion, or rather inverse Turaev torsion, as a function of these spin C structures. So you already see that this structure of Q-series invariants allows you to play with them and compose them in various combinations, maybe some, sometimes not some, over these additional labels. And later on, I'll show you more examples where you can recover some more interesting, less familiar invariants of free manifolds by taking suitable combinations of this atomic structure and taking various different limits. Another point that I'll try to make is that this Q-series invariance, which can be obtained by Borel resummation or resurgence applied to the perturbative H-bar series, are actually very computable themselves. So these are also something by now very computable and fun to play with. Okay, this leads us to corresponding counterpart or first question to which I don't know the answer, which has to do with nature of coefficients of this Q-series invariance. It is expected, based on physics, that they can be explained in terms of, or interpreted in terms of counting solutions to either equations of motion in high dimensional gauge theory or counting curves in a certain Calabi-Yau setup. So these integer coefficients C0, C1, and so on can be interpreted in terms of counting certain objects. However, based on some of these interpretations, it's also expected that these coefficients may have entirely three-dimensional interpretation, especially if the problem is formulated in the language of contact geometry. Then it is expected, especially from curve counting and Calabi-Yau, that some of these coefficients may have something to do with real orbits in a three-manifold and have intrinsically three-dimensional formulation. Aside from integer powers that appear here, the overall coefficient is actually non-integer power of Q, and that also deserves special attention. It happens to coincide with a correction term that you can find among completely different subjects, such as Higard-Floer homology or in Seiberg-Witten theory. So this points to yet another direction that would be nice to investigate further. As I mentioned earlier, this Q-series invariance obtained by resurgence from perturbative series can be viewed as atomic structure which can be composed in many different ways. For instance, if you take the sum over spin C structures, just like as we did in the context of WRT invariance, but take two copies of this object's called Z hat, then you recover superconformal index of the corresponding 3D n equals 2 theory. And this is actually a very interesting prospect because it has been a long-standing problem to compute the superconformal index that takes into account both abelian contributions of both abelian and non-abelian flat connections, and can behave nicely with respect to cutting and gluing, so that it can be defined on arbitrary three-manifold. The non-abelian contribution is known as DGG index, and today there was a very nice, interesting paper by Marcus Mourinho and collaborators, and I think that we'll hear more about it from Marcus's talk tomorrow, in fact, in the context of resurgent analysis. And I think it would be interesting to investigate further connection to the superconformal index, which contains contributions of both abelian and non-abelian flat connections. Since, as I mentioned before, the Q-series invariants are very computable themselves, you can actually compute them for pretty much any manifold now, and I'll tell you some of the techniques how to do it. Here is an answer by substituting them into this formula. You find, for example, the superconformal index for surgery on a figure 8 knot. So that's a very explicit, concrete answer, and as you can see, it also has nice integer coefficients and so on. Okay. The story of resurgence and Chern-Simons theory becomes more interesting and more delicate if first Betti number of the three-manifold on which we're studying Chern-Simons theory is positive. In that case, there are infinitely many abelian flat connections, or equivalently, there are infinitely many spin C structures, and it's convenient to organize our Q-series labeled by the spin C structures in a generating function in introducing a new variable x such that a power of each coefficient of each given power of x is basically this Q series in a spin C structure that equals to the power. From the Chern-Simons point of view, this formal variable x can be interpreted as eigenvalue of the holonomy of SL2C flat connection. In fact, everything I'm telling you today is about Chern-Simons theory with rank 1 gauge group. So in a compact form, it would be SU2, and in a complex world, it will be SL2C. But generalizations to other gauge groups are also possible and interesting, and I'll mention it briefly later on. So this leads, for example, in the case of knot complements, to a version of this Q-series invariance, which can be viewed as functions or finally hyperfunctions that depend on variables Q, that's our familiar variable, that's basically the coupling constant or exponentiated coupling constant, and additional variable X, which keeps track of infinitely many spin C structures on knot complement. So here is an example of this sort of parametric resurgence, which now involves X as a parameter. We can focus on coefficient of a given power of X and ask for resurgence. What resurgent analysis tells us, what Borel resummation would give us. And like I mentioned earlier, there is a lot of data. In fact, this slide here is taken from a paper from more than 10 years ago, where perturbative data, namely H-bar expansion, was already available. And if you look here at coefficients of fixed power of X, we see that perturbative series has the form 1 plus H-bar plus H squared over 2 plus H cubed over 6 plus H to the 4th over 24 and so on. So here, without even heavy machinery of resurgent analysis, you can quickly recognize that this is nothing but expansion of exponential of H-bar, which is what we call Q. So in a similar way, you can quickly replace H-bar expansion here by powers of Q at every coefficient, at every power of X. And what you get is precisely this double expansion in variables X and Q. But again, I want to emphasize that the right way to look or think about this formula is to treat X as a formal variable. Don't try to think about this as a function of X, and view coefficient of X to the M as a Q series associated with a spin C structure M. That's the right way to think about it. In this example, for the trefoil knot, everything is so simple that you can indeed see with the naked eye that indeed perturbative series nicely resounds in a Q series. But of course, life is not as simple in more general cases, and you need various other techniques to go on. However, I want to interject this with a question, namely future direction or direction for future research, that we already start seeing how to obtain Q series by Borel resummation for both closed three manifolds as well as knot complements. So then you can ask, what will happen if you send Q to a root of unity, but don't sum over the spin C structures in many of these cases? So if you do this, it's expected that you recover more interesting invariants of three manifolds and knots that until so far actually have not featured in the physics literature. So there are some nice but somewhat esoteric invariants from physics point of view constructed by mathematicians, such as CGP invariants, ADO invariants, and Links-Good invariants, which can be obtained from these Q series invariants for either three manifolds or knot complements if you take Q to be a root of unity. One of these invariants, namely the one constructed by Akutsu, Deguchi, and Otsky, has already been checked as a limit of this Q series invariance for knot complements, but in two other cases, I leave it to you as a conjecture that this behavior holds. It's kind of non-trivial because often, as even in this case, you need to worry about normalization factors and so on. But there are also some interesting conceptual lessons here. Namely, these invariants on the right-hand side, many of them involve non-semi-simple tensor categories. That's why they're kind of esoteric and didn't feature in Chern-Simons theory, which often leads to semi-simple tensor categories. And this is actually a good lesson and fits very well with the nature of Q-series invariants on the left-hand side, which should be interpreted as quantum group invariants associated to generic Q. So if you take representation theory of a quantum group at generic Q and send Q to root of unity, what this representation theory tells you is that you get a non-semisimple rather than semisimple tensor category, and this is part of the reason why I expect these conjectures to be true. There are other lessons that we learn from quantization of Chern-Simons theory, namely for surgeries on knots and links that allow us to construct general three manifolds. It's important to understand what happens if we do cutting and gluing three manifolds along toral boundaries. When we do gluing along toral boundary, we naturally sum over states in the Hilbert space of Chern-Simons theory on a torus. And in the case of SL2C gauge group, this Hilbert space is simply quantization of moduli space of flat SL2C connections on a torus. It's an infinite dimensional Hilbert space with a basis that can be labeled by two integers, m and n, or in the dual language, C star variable x, same x that appeared before, and an integer n. This is actually quite interesting because if you compare this to cutting and gluing in Chern-Simons theory with compact gauge group, such as SU2, you probably know that we're summing over states which are labeled by elements in the root lattice, and in fact, it's a truncated root lattice. It's truncated by value of the level k. So here we see two copies of the root lattice. We're still working with rank 1 system, Chern-Simons theory, but we have two integers. And the way to think about them is that they take values in two copies of the lattice. And moreover, there is no truncation by the level. The fact that there is no truncation by the level is not surprising. After all, we're working with generic Q, so there is no integer k to impose the truncation. But the fact that we have two copies of the root lattice is interesting and is also indicating that representation theory that's governing this Q-series invariance is based on double affine algebras or toroidal algebras, which naturally have two copies of the root lattice involved. Another lesson we learned from quantization of Chern-Simons theory is that three manifolds bounded by a torus give us states in this Hilbert space which are annihilated by Q-difference separators or by Schrödinger type equations. For example, for the knot complement, this would be precisely quantum A polynomial annihilating the corresponding wave function. This in turn can be used as a fact, as a useful fact or useful tool to actually compute this Q-series invariance. So in conjunction with resurgence, this gives a powerful tool to determine this Q-series for knot complements. And then if you feed it into surgery formula, you can quickly produce answers for any surgery on any given knot K that you wish. So here is a table presenting some of the answers for hyperbolic manifolds, which are obtained by small surgeries on a figure 8 knot. All of these manifolds are hyperbolic. They're all closed. And this is an example of a Q-series, which you can see has integer coefficients. And there is an offset by fractional power of Q multiplying the whole expression that I mentioned earlier. So combination of these tools, resurgence in conjunction with Q-difference equation, allows you to determine surgeries and answers for knots for some of them. So here I list all knots up to 7 crossings, and as of April of last year, 2019, using these two techniques, one could determine all surgeries or answers for unknot, trefoil knot, figure 8 knot, 5-1 knot, and 7-1 knot. So many other entries in this table, in this list, were completely empty. And actually, I thought that 5-2 knot would be extremely complicated. So with Gerald, we started a project which involves resurgence for 5-2 knot. That was a natural next step, trying to determine, make progress on this. However, in April of this year, there was a very interesting development due to Sang-Hyuk Park, who introduced a technique that allows to compute many of these invariants in a very nice, elegant way. I'll show you a slide about this right next. And what it does, it basically here for knots with up to 7 crossings, it turns mostly empty table into mostly full table. It still has a couple of entries, such as there are a couple of knots with 6 crossings or 7 crossings, for which the problem is up for grabs, but this nice technique allows to produce the answer for many other knots and produce the corresponding surgeries. So this technique is based on the quantum group and actually is very much in the style of Reshetikhin-Turaev construction. So apart from being very fast and efficient in terms of computations, like I said, it basically fills much of this tables for knots with up to 7 crossings. I think it also conceptually is one of the most promising ways to think about this Q-series invariance, because it works directly with our matrix and quantum group at generic value of Q. So mathematically, this is definitely one of the promising ways to think about this problem. So we talked a lot about knot complements, but the theorem that I mentioned earlier says that any 3-manifold can be obtained by performing surgery on a link. So therefore, it's important to understand links and their complements. And using current techniques, one can understand some of them. For example, if we take figure-8 knot and form a link with a bunch of unknots, this is something which is well understood by now. Similarly, if you take a link made out of 2 trefoils, this is also a check mark. But more complicated links, such as Borromean rings, still remain as a question mark, and this is obviously one of the next important directions to pursue. There are other problems which I list as open questions. For instance, the physics approach to resurgence clearly suggests that we should expect poles on the Borel plane to be precisely at the values of the Chern-Simons functional on our 3-manifold. So this is, of course, what's expected, and this is very natural. But if you go further in the list of examples to more interesting and complicated ones, you soon encounter something funny. For example, this phenomenon, which I believe first appears if you consider fairly advanced knot, namely 5-2 knot, and consider 0 surgery. So this is an example of a manifold with B1 equals to 1. So then you find that indeed poles on the Borel plane are very much aligned with values of the Chern-Simons functional, just as you expect, but there is a peculiar shift by 1/8, which so far appears in a somewhat mysterious form and has no clear explanation. So I believe that this phenomenon, this peculiar phenomenon of the shift by 1/8 is related to the fact that 3-manifold has first Betti number equals to 1, but I don't know the origin of the shift, and obviously that's why I phrase it as a question for future research. And finally, my last question or direction naturally progresses from knots to links and then to trivalent graphs. So we talked about knots, knot complements, and capping them off in a surgery operation. Then I posed the question about links with more components. And natural in the sequence is to study graphs and graph complements. So here is an example of a trivalent graph, often called theta graph, because it looks like Greek letter theta. Its complement is a genus 2 handle body. And in fact, gluing such handle bodies gives yet another universal construction of 3-manifolds. Namely, any 3-manifold can be constructed by gluing handle bodies of some genus. So therefore, this would be yet another interesting direction to develop and understand. And in the case of the theta graph, if you try to do parametric resurgence, similar to what we did for knots and links, you see that something interesting is happening. Namely, powers of the color here is n, or that's the dimension of representation by which these Wilson lines are colored, actually grows faster than power of the coupling constant. You already see it in the first 2 terms. So this is something peculiar, and similar phenomenon would naturally appear if you study also knots and links with general values of the framing. So these 2 problems are actually closely related. So I leave it as an open problem to study such resurgence for Chern-Simons theory on graph complements and develop a Hilbert decomposition approach to the corresponding Q-series invariants that we discussed today. So these are 5 prospects and 5 problems, and I thank you for your attention.
Well, thank you very much, Sergei, for a great talk. So we have 15 minutes for discussions. So any questions, please raise your hand. Oh, okay. So Arkady has a question. Arkady, please unmute yourself. And
thank you. Hello, Sergei.
Hello.
I'm not sure if you see me. I probably okay, but you know, you know that I'm used to ask stupid questions, so I'm sorry to try this again, right? But I just trying to understand in terms of we discussed before a lot, but I still cannot get it at the end. You know, when we are talking about Chern-Simons in a simple form, you know, it's kind of a usual analog would be like you know, kind of degenerate level in quantum mechanics, right? Some few states. So Hilbert space is like a limited number of states, right? But my impression is that when you are discussing this, that it is more complicated object, so it's not like a quantum mechanic even, but like something associated with field theory as well, right? When you're calculating these higher orders, right? I'm trying to check this.
Well, this problem is, I would say, closer to full-fledged gauge theory than to quantum mechanics. For Chern-Simons theory with compact gauge group and fixed level, which is integer, it indeed has finitely many states, so the Hilbert space is finite dimensional. But the problem that appears here involves infinite dimensional Hilbert spaces, and the fact that space of gauge connections on our space-time manifold is non-simply connected plays an important role, and so on. So this is the reason why I personally view Chern-Simons theory as a really good example of gauge theory. It just happens that using these tools from topology and interplay, we can compute many perturbative coefficients.
But in some way, it is a field theoretical part of it is kind of hidden, right? So you have a, you know, a phase which is look like a few levels, right? I mean, quantum mechanical levels, and behind this is this kind of you know, all this machinery you are talking about, right? So I agree that it's there inside, right? But I don't know. When you are talking about the Hilbert space, right? Your Hilbert space is not infinite, contains not infinite number of states, right?
It is. It contains infinitely many states. Yeah.
Yeah, infinite. Yeah. I see. So in this way, that okay. Thank you.
Yeah. Yeah.
all right, Ovidiu. Okay.
Yeah, I'm not an expert in Chern-Simons, but I found this fascinating.
Ovidiu, we can barely hear you.
Is it better now?
A little bit.
There's something with the microphone. Let me try to see if I can do something quickly here.
I can hear you now. I can hear you now.
It's better now, yeah. Maybe it was on my end.
Okay. Yeah. So I said I'm not an expert in Chern-Simons, and I found all these things fascinating nonetheless. My first question is what exactly is the source of resurgence in this kind of problems? Is it the path integral formulation, or you have a simpler generator of resurgence? That's my first thing.
Yeah, so this is what I tried to explain very briefly in the beginning, that you can view this problem as general quantum field theory. So then of course you can compute Feynman diagrams and produce perturbative series by very laborious hard work of Feynman diagram computation. So that usually is doesn't get us beyond, say, 4 or 5 loops in typical gauge theory, and even then, when we're lucky. But what happens here in Chern-Simons theory is that these perturbative computations can be performed to arbitrary loop level using additional techniques. So that's where this topological nature, the fact that Chern-Simons theory is halfway between gauge theory and QFT and halfway between topology actually helps. So using some of this.
But still, in some sense, it's an infinite dimensional problem at the origin.
Exactly, yeah. So I think it's a perfect sweet spot which shares some of the features of real full-fledged QFT and is also very computable. That's how we get hundreds of loops at perturbative expansion.
And the other one is just a curious thing. So I noted in many of those expansions sort of similarities with the Q expansions of theta functions. Is there a deeper connection there? Or?
I think so, because for some of these knot and link complements, the results which appear, for example, this Q series is sometimes actually a theta function. So if most likely, if you give me some particular theta function, it will be possible to find a 3-manifold, which gives, if not exactly the same, something very, very close. And by now, there are many classes of interesting functions, such as theta functions, false theta functions, mock theta functions, which can be realized as such Q-series invariants of various 3-manifolds.
Yeah, very interesting. Thank you very much. Thank you.
Thank you.
Okay, Marcos?
Yeah. Hi, Sergei.
Hi, Marcos.
Well, a very inspiring talk. Thanks a lot.
Thank you for staying awake.
Yeah, he's almost 1 here. He's already past 1 here, almost. So one question. You could get different Q series which have the same perturbative expansion in H bar, right? I mean, in principle, this radial asymptotics is not doesn't uniquely define the Z hat. So how do you actually pick the particular Z hat which is appropriate for the perturbative series? I mean, is there really a well-defined procedure? Because in principle, you could write different Q series with the same asymptotics.
That's right. That's a very good question. So that's why from a resurgence point of view, this is really important, and this is deep. So thank you. That's a really good and delicate question. I don't have a full answer to this, but what happens is that from resurgence point of view, you indeed typically need some additional information, such as choice of contour or some additional input data, which we already encountered even in simple examples that you and I and Pavel studied a couple of years ago. But what happened recently is that there were various other approaches to find this Q series, which are mostly rooted in the fact that it should behave really nicely under cutting and gluing. So that somehow determines uniquely this Q series, and then it's easy to check that it has the right asymptotics, but the flow of information in some sense is backwards. So I think now that there are so many computational tools to find independent definition of this Q series, it would be good to revisit the problem of resurgence, even in those contexts where, in those examples where we know what the Q series is.
I see. That's very good answer. Thank you. Thank you.
Thank you, Marcus.
Right. Okay. Yuya.
Yeah. So I want to ask a question about the shift of renormal pole compared with the real renormal pole and the action of value of the Chern-Simons action. So, for example, so can we understand this shift of 1/8 by, for example, some the effect of the zero mode integration for the Gaussian integral around Chern-Simons value? Or so do we have a way to understand this shift from path integral viewpoint?
No, I don't. That's why I present. I suspect the answer may not be terribly complicated, but I don't know the explanation, and that's why I presented here as an open question. I don't think this is something terribly simple either, but it's probably not super involved. At least I hope not. So I don't know the answer.
I see. That's very interesting. Thank you very much.
Okay. Mithat has a question.
Okay. Thank you, Sergei, first of all, for the nice talk. My question is, we know that the gradient flow equation in the complexified version of the Chern-Simons theory is related to the instanton equations in the topologically twisted unequal force for Yang-Mills theory, right? Mm-hmm. So does these ideas on Chern-Simons theory, do they help somehow in the unequal force for Yang-Mills theory?
I hope so. And I hope, in fact, both ways they could, perspective from twisted unequals for super Yang-Mills could help understand some of the properties of this Q series better, and vice versa. Hopefully this Q series could teach us something about moduli spaces of solutions in this twisted unequals for super Yang-Mills. For instance, I mentioned several invariants which were known before, although not in the physics community, such as Links-Good invariants, ADO invariants, or CGP invariants that are expected to be limits of this Q series and various combinations. So another simple invariant that of three manifolds that's labeled by spin structures, not spin C structures, but something closely related, namely spin structures, is Rochlin invariant. It's roughly 60 years old, and it's an interesting invariant of a three manifold. But I suspect that that particular invariant, which also appears as some limit of this Q series in particular case, could be best understood using that gauge theory description. So therefore, I also hope that there is a lot of interaction and collaboration between these two descriptions.
So I see there may be some cross-fertilization there, you are saying.
Yeah, I hope so.
The Hilbert space of the 4D theory. Okay, thank you very much.
Other questions from anyone? I have a question. So about this renormal shift 1/8. Do you know what happens to that 1/8 for a higher rank gauge group?
Oh, that's a good question. I think the data is available, but I don't know if anybody has looked at it. So that's a good question. I don't. Indeed, maybe by looking at families, namely labeled by rank, will provide some clue what the shift is. Again, to me, it's a mystery. So I offer it as an open question, and I'm sure some of the smart people on the call probably will solve it soon.
Hopefully. Thank you. All right. So we still have 5-6 minutes. We already tested Paolo's screen sharing, so everything works well. Okay, I guess we'll wait for a few more minutes and continue with the second talk.
Yeah, thank you everyone for coming. Thank you.
Thank you.
Thank you, Sergei, for an excellent talk.